Let's start with what you were taught. Entropy is disorder. Low entropy means organized, structured, neat. High entropy means scattered, random, messy. The second law says the universe always moves from order to disorder. That's why ice melts. That's why your desk gets cluttered. That's why everything falls apart. Neat story, completely useless. Here's why. What does disorder mean? Not philosophically, physically. If you're going to claim that entropy measures disorder, you need to tell me what disorder is in a way that doesn't depend on what you personally find messy. Take a deck of cards, shuffle it. Now it's disordered, right? High entropy. But compared to what? Compared to the deck sorted by suit and rank, ace to king, clubs to spades, that's the ordered state. But why is that ordered? Because you decided it was. Because that arrangement means something to you. To the universe, to the atoms in the cards, there is no difference. A shuffled deck and a sorted deck are both just 52 pieces of paper in some configuration. Neither is more special than the other, unless you're the one judging. Now take the same shuffled deck. Show it to a magician who memorized that exact sequence. To them, it's not random. It's the arrangement, perfectly specified, low entropy. Same deck, same physical state, different entropy depending on who's looking. That should bother you, because if entropy is supposed to be a fundamental property of physical systems, something the universe does it shouldn't change based on whether you think something looks tidy. The second law of thermodynamics is not a housekeeping rule. It's not an aesthetic preference. So either entropy isn't about disorder, or disorder isn't what you think it is. Feynman knew which one it was. Feynman hated the word disorder. He didn't just dislike it. He actively tried to eliminate it from how people talked about entropy. Because every time someone says entropy is disorder, they're smuggling in human judgment and calling it physics. Here's what he said instead. Entropy is about counting, specifically counting microstates. A microstate is a complete specification of a system. Every particle's position, every particle's velocity, the exact configuration down to the smallest detail. For a gas in a box, a microstate tells you where every single molecule is and how fast it's moving at a given moment. Now, most of the time, you don't know the microstate. You can't. There are too many particles. So instead, you know the macrostate, the big picture stuff, temperature, pressure, volume, the things you can measure without tracking 10 to the 23rd molecules. Here's the key. Many different microstates correspond to the same macrostate. If the gas fills the whole box evenly, there are an absurdly large number of microstates that all look like gas spread evenly throughout the box. The molecules could be in trillions of different exact positions, and you'd never know the difference. Same temperature, same pressure. But if all the gas is squeezed into one corner, there are far fewer microstates that match that description. The molecules have to be in very specific positions to all be bunched up in the same region. Entropy, in Feynman's terms, is a measure of how many microstates correspond to the macrostate you're observing. More microstates? Higher entropy. Fewer microstates? Lower entropy. New disorder. No mess. Just counting. The second law, then, isn't about the universe becoming chaotic. It's about the universe exploring configuration space. And there are vastly more ways for a system to be in a high-entropy macrostate than a low-entropy one. Not because nature prefers disorder. Because math prefers larger numbers. When you release gas from a corner, it spreads out. Not because spreading is more disordered. Because there are overwhelmingly more microstates where the gas is spread than where it's bunched. The system isn't seeking chaos, it's seeking probability, and probability doesn't care what you think looks messy. Let's do a thought experiment. You walk into a room, clothes on the floor, books scattered across the desk, papers everywhere. High entropy, you think, disordered. But now imagine someone else walks into the same room, a forensic investigator. They look at the clothes and see exactly where someone stepped out of their shoes. They look at the books and see the sequence in which they were read. They look at the papers and see a trail of thought, a workspace mid-process. To them, this is not disorder. This is information. This is a highly specific arrangement that tells a story. Low entropy, same room, same physical configuration, different entropy. You might object, that's not how entropy works. Entropy is objective. It doesn't change based on interpretation, but it does, because entropy isn't a property of the room. It's a property of what you know about the room. If you know nothing about why the clothes are where they are, then from your perspective, there are countless microstates consistent with clothes on the floor somewhere. High entropy. But if you know the exact reason each item is in a specific position, if you have that information, then there's only one microstate consistent with your knowledge. Low entropy. Here's another version. 2 boxes of gas, both at the same temperature and pressure. Identical macrostates. You'd say they have the same entropy. But now imagine that in one box, you've secretly tagged every molecule. You know exactly which molecule is which. You've tracked their positions from the start. Does that box still have the same entropy as the other one? No. Because entropy is not about the gas, it's about your information about the gas. The tag box has lower entropy to you because you've reduced the number of microstates consistent with what you know. You've collapsed uncertainty. The gas itself hasn't changed. The molecules are doing the exact same thing, but the entropy you assign depends on whether you're tracking them. This is not a trick. This is what entropy is. It's a measure of how many possible microstates are consistent with your macroscopic knowledge. When you don't know much, entropy is high. When you know more, entropy is lower. The universe doesn't have one entropy. You assign it an entropy based on your ignorance, and that changes everything. This is where it gets uncomfortable. You want entropy to be out there, a real thing, a property the universe has independent of whether anyone's watching, like mass or charge or energy. But it's not. Entropy is a bookkeeping device. It quantifies missing information, and information is not a vague concept here. It's precise. It's mathematical. Claude Shannon built an entire theory around it in 1948, and it turns out his formula for information entropy is identical to the thermodynamic entropy Boltzmann wrote down 70 years earlier. That's not a coincidence. When you don't know the microstate, you have uncertainty. That uncertainty can be measured. Entropy is that measurement. It's how many yes or no questions you need to ask to fully specify the system. How many bits of information you're missing. Let's make this concrete. You flip a coin but don't look at the result. It's either heads or tails. You're missing one bit of information. That uncertainty, that's entropy. Now flip 1,000 coins. You don't know the outcome of any of them. You're missing 1,000 bits. Higher entropy. But if someone whispers to you, they're all heads, suddenly you're missing 0 bits. Entropy drops to 0. Not because the coins changed, because your knowledge changed. The coins are still sitting there. The physical state is the same. But the moment you learn the configuration, the entropy collapsed. This is not metaphorical ignorance. This is literal thermodynamic entropy. When a gas expands into a room, it's not that the molecules become disordered. It's that you lose the ability to track them. You don't know which molecule went where. The information about their specific trajectories is no longer accessible to you. That lost information is the increase in entropy. The second law, then, is not a law about the universe becoming messier. It's a law about you losing information over time in systems with many particles. It's easier to forget than to remember. It's easier to lose track than to keep tracking. Entropy increases because ignorance is the default. Knowledge requires effort. It requires tracking, measuring, recording, and in any real system, that effort has a cost. You can't just know where every molecule is. The act of finding out disturbs the system. The act of recording the information generates heat. Ignorance, on the other hand, is free. So when you watch ice melt, you're not watching the universe decay into disorder. You're watching your ability to distinguish microstates disappear. The molecules are still there, still obeying perfectly reversible laws. But the specific arrangement that made it ice has dissolved into a configuration space so large you can't point to it anymore. The universe didn't forget. You did. In 1867, James Clerk Maxwell imagined a demon. Not a real demon, a thought experiment. A tiny, intelligent creature sitting at a door between two boxes of gas. The gas molecules are bouncing around, some fast, some slow. The demon watches them. When a fast molecule approaches from the left, it opens the door and lets it through. When a slow molecule approaches from the right, it lets that through too. Fast molecules on the right, slow molecules on the left. After a while, one box is hot, the other is cold. The demon has separated the gas by temperature without doing any work. No energy input, just observation in the little door. And that, Maxwell realized, violates the second law of thermodynamics, because entropy should increase. The gas should stay mixed. Temperature should equalize. But the demon has reversed it. It's created order, low entropy from disorder, just by knowing which molecules are which. For decades, this was a paradox. If entropy is just about information, and the demon has information, why can't it decrease entropy for free? What's stopping it? The answer came from Rolf Landauer in 1961, and it's brutal. The demon can't remember forever. To keep operating, the demon has to record which molecules are fast and which are slow. It has to store that information somewhere in its brain, in a notebook, in a memory register. But memory is physical. It's made of molecules, and memory is finite. Eventually, the demon runs out of space. It has to erase old information to make room for new observations, and erasure has a cost. When you erase one bit of information, when you reset a memory from 1 to 0 or heads to unknown, you have to dump that information somewhere. It doesn't just vanish. It gets converted into heat, into random molecular motion, into entropy. Landauer's principle, erasing information, increases entropy by at least a specific minimum amount. It's not negotiable. It's not an engineering problem. It's fundamental. So yes, the demon can decrease the entropy of the gas by sorting molecules, but it increases the entropy of its own memory by at least as much. The total entropy of the system gas plus demon still goes up. The second law survives. But notice what just happened. The second law holds because information is physical. Because knowing something, remembering something, erasing something, all of that is a thermodynamic process. Knowledge isn't free. It has weight. It has heat. It has entropy. You can, in principle, decrease entropy locally. You can sort molecules. You can unmix a gas. You can make ice in a freezer. But only if you're willing to pay the informational cost elsewhere. Only if you're willing to increase your ignorance somewhere else in the system. The universe doesn't forbid order. It just makes you pay for knowledge. And the price is always entropy. So let's say it plainly. The second law of thermodynamics is not a statement about the universe. It's a statement about observers. It says, if you are a macroscopic being who cannot track individual microstates, then over time, the systems you interact with will evolve toward macrostates that correspond to more microstates, which means from your perspective, entropy increases. But that from your perspective is not a footnote, it's the entire point. The universe at the microscopic level is reversible. Newton's laws are reversible. Schrödinger's equation is reversible. If you filmed a single particle bouncing around and played the footage backward, you couldn't tell the difference. The physics works both ways. There is no fundamental law that says thou shalt become disordered, but you are not watching individual particles. You're watching trillions of them, and you're summarizing their behavior with a handful of variables: temperature, pressure, volume. You've thrown away the details. You've chosen ignorance because tracking every molecule is impossible. And once you've done that, once you've committed to describing the system macroscopically, the second law becomes inevitable. Not because the universe prefers high entropy, because you can't tell the difference between the vast majority of microstates that all look the same to you. When gas expands into a room, it's not seeking disorder, it's exploring microstates at random. And the overwhelmingly likely place it ends up is a macrostate you describe as evenly spread out, because there are so many more ways to be spread out than bunched up. The universe doesn't know which macrostate it's in. You do. And you lose track. Here's the thing: if you could track every molecule, entropy wouldn't increase. If you were Maxwell's demon with perfect knowledge and infinite memory, you could watch the gas expand and then reverse every collision, send every molecule back exactly where it came from, and reconstruct the original state. No entropy increase, perfect reversibility. But you can't. You don't have that information. You didn't record the trajectories. You can't reverse what you never tracked. Entropy increases because you are not omniscient. The second law is not a law of nature. It's a law of perspective. It's what happens when beings with limited information try to describe systems with unimaginable complexity. And that's why Feynman insisted, stop calling it disorder. Disorder implies the universe is doing something. The universe is just evolving. You're the one who's lost. Entropy is the measure of your confusion. It increases because confusion is easy and clarity is hard. Because forgetting is passive and remembering is active. Because the default state of any observer in a complex system is ignorance. The second law is about you, and it always has been. There's a film playing in reverse. Smoke flows back into a cigarette. Shattered glass leaps off the floor and reassembles into a cup. A puddle of water crawls upward and freezes into an ice cube on the counter. You know immediately that the film is backward. These things don't happen. Entropy doesn't decrease. Time doesn't run that way. But here's the problem. The molecules don't know that. Every single collision between molecules in that video is perfectly reversible. If you zoom in far enough, down to the individual atoms, there is nothing in the physics that forbids the reverse process. Newton's laws work backward just as well as forward. If you took every molecule in the smoke and reversed its velocity, just flipped the direction, kept the speed, it would flow backward into the cigarette, frame by frame, exactly as shown. The physics allows it. The reason it doesn't happen is not that the universe forbids it. It's that the specific initial conditions required are absurdly unlikely. You'd need every molecule in the smoke to be moving in exactly the right direction at exactly the right speed. Trillions of particles, all perfectly coordinated, and you don't have that information. You didn't record where each molecule was. You didn't track their velocities. You lost that information the moment the smoke dispersed. So you can't set up the reverse. You can't undo it, not because the universe forgot, because you forgot. The arrow of time, the thing that makes the future feel different from the past, is not built into the microscopic laws. It's built into you, into your ignorance. When you see smoke spreading, you're not seeing the universe obeying some cosmic rule about disorder. You're seeing the consequence of not knowing the microstate. The entropy increases because you can't distinguish between the astronomical number of microstates that all look like smoke everywhere. But if you did know the microstate, there would be no arrow. You could, in principle, reverse everything. There's an even stranger consequence. Imagine you take a video of gas expanding in a box. You show it to someone and ask, is this playing forward or backward? They can't tell. Because at the level of individual molecules, both directions are equally valid. There's no timestamp on the collisions, no preferred direction. The only way you know the video is playing forward is if you already know the gas started bunched up in the corner. You need the boundary condition. You need to know the initial macrostate, and that's the only reason entropy increases, because we live in a universe that, for reasons we don't fully understand, started in a low entropy state. The Big Bang was not high entropy. It was incredibly, incomprehensibly low entropy. All the matter and energy packed into a tiny region, highly structured, far from equilibrium. Ever since, the universe has been relaxing, spreading out, exploring configuration space, not because it's becoming disordered, but because there are more ways to be spread out than concentrated. But the microscopic laws never changed. Every interaction is still reversible. The universe hasn't forgotten anything. You have. Entropy is the shadow of your limitations. It's the gap between what the universe knows, every position, every velocity, every microstate, and what you know, which is almost nothing. The second law doesn't say the universe becomes disordered. It says that if you're not omniscient, you'll lose track, and you always will. Eventually, they say the universe reaches maximum entropy. Heat death. The end state. Every star burns out. Every black hole evaporates. All matter spreads thin across an ever-expanding void. The temperature everywhere becomes the same. No gradients, no flows, no differences left to exploit. Maximum entropy. People call it the death of the universe. They picture a cold, lifeless, featureless expanse. Total disorder. The final victory of chaos. But that's not what maximum entropy means. Maximum entropy means maximum indistinguishability. It means that every microstate looks the same from the outside. There are no macroscopic features left that let you tell one configuration from another. The universe hasn't become chaotic. It's become smooth, uniform, unknowable. Not because there's nothing there, because there's no way to tell what's there. The particles are still there, still moving, still interacting. The information is still encoded in their positions and velocities, but from any macroscopic perspective, it's invisible. Every measurement you could make would return the same result. Every region of space looks like every other region. You've lost the ability to distinguish, and that's what entropy is, the measure of how much you cannot distinguish. At maximum entropy, you can't distinguish anything. The universe doesn't die. Your ability to describe it dies. Because description requires difference. It requires contrast. Hot versus cold, dense versus sparse, structure versus background. When everything is the same, there's nothing left to say. Feynman understood this. Entropy is not about mess. It's about the collapse of meaningful description. It's about the point where all the information is still there, but none of it is accessible from the outside. Here's the unsettling part. The universe at heat death is not less ordered than it is now. It's not more random. It's not more chaotic. It contains exactly the same amount of information, encoded in exactly the same number of microstates. But you can't read it anymore. The second law doesn't say the universe becomes disordered. It says that distinguishable macrostates evolve into indistinguishable ones. That differences erase themselves. That the features you can measure fade into equilibrium, not destruction. Erasure of contrast. And maybe that's the real discomfort. Because entropy isn't something happening to the universe, It's something happening to the relationship between you and the universe. It's the drift toward a state where your questions stop mattering, where the system stops answering. The universe will still be there at heat death, every bit as full of information as it ever was. You just won't be able to tell. And in the end, entropy is not the measure of disorder. It's the measure of silence.